Welcome to part 2 of the earthquake notes. So we talked about how seismology is the study of earthquakes. And so what records an earthquake, or at least the earthquake magnitude? Well, that's a seismograph. And seismographs are used to determine the magnitude of an earthquake. So what is magnitude? Well, magnitude is the strength of an earthquake, or basically it's the earthquake size. Now, the Richter scale is actually a scale, and there's a modified Richter scale, there is an updated Richter scale. But basically, the Richter scale compares earthquakes' magnitudes. And they typically range from a 1, which is minor, to an 8.9. Now, can they go above 8.9? Yeah, they can get into the 9s. Some people constantly ask, well, how large can they get? And I guess there really is no upper limit. Now, when we start talking about them, we're going to start talking about how it's exponential, how a difference between a 1 and 2 is a lot more than just a difference of 1. It's 1 time larger. It's actually quite a bit larger than that. So once you start getting into the 9s and going to the 10s and 11s, it's not that easy to get an earthquake that large. But if something major would happen, we could get a higher and higher earthquake. So there is really no upper limit. Now here's Charles Richter, and he was instrumental in developing the Richter scale. And each increase of 1 equals a 10 times increase in the ground movement magnitude. And for example, if you go from a 4 to a 5, it represents a 10 times increase in the ground movement magnitude. A 4 to a 6 represents a 100 time increase in the ground movement magnitude. Now, there's a different way of looking at it too. Each increase of 1 is also equal to a 30 time increase in energy being released. So now if we go to a 4 to a 5, it's 30 times more energy that was being released. You go from a 4 to a 6, it's 900 times more energy being increased. Now, this number 30, I just want to point out that depending on what book you read, this number does vary. I've heard that being 31. I've heard it being somewhere between 30 and 31. So you will see different numbers for this. But either way, this is a significant increase. So just a difference between a 4 and a 5 is a 30-time increase. Now, what do we call it when we go from 30 to 900? Remember, we've covered this in math class. It's actually called exponential growth. So let's look at earthquakes. These great earthquakes that are typically 8 and higher. How many on average do we have? On average, there's approximately 1. How many major earthquakes? 7 to 7.9. We have about 17. And then strong earthquakes is about 134. Now, a lot of these light earthquakes, you can kind of feel the light earthquakes, especially if you know they're coming. But once we start getting into these minors and very minor earthquakes, they're just so small we don't feel them. So it's not when we come down here where it says 1,300,000, we don't necessarily feel every one of those earthquakes. We usually don't feel them all. But once we start getting into the high 3s, into the 4s, this is where we're going to start to feel them. So one of the reasons why they're estimated is there's just so many of them, it's hard to record them all. Now, one of the common questions asked, or that students will ask me, is, Mr. Rattoon, if we have several of these happening in 1 year, and it seems like there has been a lot of these happening, does that mean earthquakes are on the rise? No, it's an average. So we might get 5 of these in 1 year. The next year we might not get any. Then we might get 1. Then in the next 2 years we might not have any. So over time we average 1, what they call great earthquake, 8 and higher a year. So where did the largest known earthquake occur in the past? Well, it actually happened in Chile, and some geologists, recorded it at about an 9.5, and it was the largest known earthquake, and it resulted in over 6,000 deaths. It actually triggered a tsunami or seismic wave, and a lot of times people incorrectly call that a tidal wave, but it's called a tsunami. And we're actually going to talk more about tsunamis at the end of the notes. But here's the interesting thing. It actually killed people as far away as Hawaii and Japan. And one of the reasons for that is that the tsunami can actually travel for thousands and thousands of miles. It can actually travel as fast as a jet airliner. And so people who were out on the beach and in Japan, if they were out there and they didn't know this tsunami was coming, this giant wave, that's how they died in places like Hawaii and Japan. And one note, that Chile also lies in a subduction zone, and that's why they have major earthquakes happening in Chile quite frequently. So what was the greatest number of people ever killed in one earthquake? Well, this actually happened in China in 1556, and it's estimated that about 830,000 people died. Now, I've seen different numbers. I've seen numbers as low as 813,000 people. So, you know, that's a few thousand difference, but still, 830,000. If you look at Wisconsin, that's like all of the city of Milwaukee dying in one of these earthquakes. Now, you might ask, did all of these people die in just the earthquake, the ground shaking? No, a lot of these people died as a result of fires, structures toppling on them. And also, a lot of times after earthquakes happen, it ruins the economy, it ruins the agriculture, and a lot of people can't feed themselves, so starvation also ends up killing a lot of people, as well as things like tsunamis. So there's lots of different factors. It's not the actual earthquake, the earth trembling that kills most people. It's the other little things that kill people. This dashing man right here is actually Mercalli, and he also came up with a scale, and he called it the modified Mercalli scale. And it expresses the intensity of an earthquake's effect on a given locality. So here it's not necessarily looking at the magnitude, but it's looking at its effect on a given region or a given location. And it's expressed in Roman numerals from 1 to 12. And with this, 1 is not felt at all, and a 12 would be total damage. And here's the interesting thing. Evaluation of earthquakes' intensity can only be made after eyewitness reports and results of field investigations are studied and interpreted. So you're not actually going to get this rating until after the earthquake happens. Scientists will have to come in, they'll have to look at what the damage was, how the ground moved, and then they'll rank it on a scale of 1 to 10. When we look at the great earthquake of San Francisco that happened in 1906, and the New Madrid Fault quaking in 1812, these earthquakes reached a maximum intensity of 11. So they weren't even as bad as they could have been. Here's the earthquake of 1964, and on the modified Mercalli scale, it was ranked a 10. So you can see that there's quite a bit of destruction. The magnitude that was high. It was about a 9.2. But when we look here, so here's someone walking down on a sidewalk. So this sidewalk should be way up here level with this area up here. So it's hard to really estimate this, but I mean, you're looking at maybe 2 or 3 cars stacked on top of each other. So you're looking at a good 15, 16 foot drop here. So that was only a 10. It wasn't even an 11 or a 12. So here's one of the reasons why we need a modified Mercalli scale. If you look right here, this is where the earthquake happened. So if I was trying to, if I was trying to send rescue crews and fire departments and water and food, I might be tempted to send everything here because this is where the earthquake happened. But if I look at where the damage occurred, if we go back up here to San Francisco and Oakland, you see there's some 9s. So if I was sending in aid, I would send aid here, but I would also start to send aid up to this area because they also had significant damage. And when we look at the scale down below, you're looking at 30 to 40 miles away. So again, the modified Mercalli scale looks at its effect on a given region, its effect on the people, and not just pure size or magnitude of an earthquake. So earthquake damage factors. What are some of the things that determine earthquake causes? What are some of the things that will cause earthquakes to be more severe? First of all, the earthquake magnitude. Obviously, the higher the magnitude, the more damage you're going to have. And this makes sense. Also, the location. One of the greatest earthquakes of all time actually happened in the middle of nowhere. It happened in the middle of a jungle. And as a result, there was very little damage. People weren't living in the area. So obviously, the earthquake, even though it was very, very large, no one really noticed it. But if that same earthquake would happen in a major metropolitan area, now all of a sudden you'd have more damage and more people would notice. Or if a smaller earthquake happened in the middle of a major metropolitan area, that smaller earthquake would do more damage than a larger earthquake that happened in the middle of a jungle. The design of buildings and other structures. Now, you go to places like California, you go to Southern California, Los Angeles, San Francisco, they have pretty strict building codes. And these building codes require them to build seismic safe structures. Now, are they going to be completely seismic safe? No. Nothing can survive a very severe earthquakes. But the smaller trembles, the smaller earthquakes can't, a lot of buildings can be designed to withstand it or to have minimum damage. But you go to some places where they don't have these same building codes. Go to places like Haiti. One of the reasons why there are so many fatalities in Haiti, because they didn't have the strict building codes that they did in places like Los Angeles. Types of ground on which the structures are built. When we talk about liquefaction a little bit later on, we're going to find out that loose packed material, you're going to have a lot of severe damage. Whereas if you can take the pilings, or the structure, if you can build it right down to the bedrock, there's going to be less damage that takes place. And are you prepared for disaster? Are you ready for all the damage that's going to occur? If these are all done, you're going to have less damage. But if you're not prepared, then you will have more damage. So I just mentioned liquefaction briefly. What is liquefaction? We're actually going to do a lab on liquefaction. This is a phenomenon in which the strength and stiffness of a soil is reduced by earthquake shaking. So look at this picture that you see right here. You can see that these structures, this building, these aren't dominoes. This entire building was normally straight like this, but the whole thing just fell flat on its side. And that's because of liquefaction. Solid ground, if it's saturated with water, can act much like a liquid. And obviously buildings aren't going to be able to stand up in ground that's a liquid. So part of the building fell over, or at least one side of it fell over. You can see these other ones that are leaning in that way. Eventually these are going to fall over, or they're going to have to tear them down because there's no way people can live in them anymore. Here's another one. I like this one right here. So this house used to be flat here, but once the earthquake started shaking, this whole foundation just sank into the ground. Look at this hospital. You can see right here that it used to come straight out here. Or this, you might look at this and say, oh, 1 story, 2 stories, no big deal. But look over here. There's 1, 2, 3 stories and a garage. So most of that has collapsed. Or, golly, this car used to look like it used to be a van. Now it's a compact car. So at least you'll have some better parking privileges and you can park in compact car spaces. But all these structures were damaged because of liquefaction. Here again, this is in the Marina District in the San Francisco area. And a lot of this area, even though it looks like it's solid ground, a lot of this area was reclaimed from the marshy areas right next to the bay. They would put fill in there, and then over time, people would grow, or people would build, they wouldn't grow, but people would build on top of this filled-in marsh area, thinking, oh, it's good building area. But once an earthquake happened, because it was not compacted enough and because it was saturated, that solid ground actually acted much like a liquid and liquefaction happened. Let's take a minute to talk about Wisconsin and earthquakes. Again, we probably aren't going to ever experience a major earthquake in Wisconsin, but you never know. Have earthquakes happened in the past? Yes. A few years ago, Mr. Phillips and I, we attended a seminar down in Mount Horeb, and they have a storage area for a lot of the geology samples taken around the state. And one of the samples that they showed us actually had a fault running through it. So that was interesting to see. Also, if you remember, it was last year, and right now it's 2012, so you're looking at 2011. And it actually made national news. There was some noises happening in Clintonville. And these noises, it sounded like moaning, and people really couldn't figure out what it was. And the last I heard, some of the geologists were actually theorizing that it was the ground that was moving, that was shifting, causing this moaning sound. So it wasn't necessarily a major earthquake, but there was enough movement, to create these sounds, almost like a booming sound that was happening. Now, where is our closest major earthquake zone to Wisconsin? Well, it's probably the New Madrid Fault. Right down here, southern Arizona, or not Arizona, but southern Illinois. You've got Missouri, Arkansas, you've got Tennessee, Kentucky. And scientists estimate that there is a 9 in 10 chance of a major earthquake happening sometime within the next 50 years. And the NMSV is New Madrid Seismic Zone. So in the next 50 years, when could it occur? It could occur right now. Did you feel it? How about right now? Did you feel it? Well, it might not occur right now. It might occur tomorrow. It might occur next week. It might occur in 50 years. And now there's only a 9 in 10 chance that it could happen within 50 years. It might be 75 years. We just don't know. It's hard to predict earthquakes. In fact, very few earthquakes have ever been predicted. In fact, I don't know of any that have been truly predicted. Several people have claimed to have been able to predict earthquakes, but that's a whole nother story. And proving that they were actually able to predict it versus just me saying, did it happen now? Oh, yep, it happened now and afterwards. Because eventually someone's going to be right if they say, oh, yep, it's going to happen sometime in the next week. Because eventually it's going to happen. So what happened with the Madrid Fault? And a lot of it comes from what we call a real foot rift. At one point in time, the continent, or the crust underneath Arkansas, Missouri, and here's your New Madrid. At one point in time, the crust actually started to rift apart, move apart. And for some reason, and scientists don't really understand why, it stopped. And so they theorize that a lot of this faulting, a lot of this earthquake is happening as a result of that, where there's still some shifting going on with the different plates. It's not as if it's still moving apart, that there's going to be a new ocean being created here with this rifting, but the idea that it is moving apart, that it is still shifting, not necessarily moving apart, but just shifting. And so until it's completely settled, there's going to be some earthquakes there. There's going to be earthquakes happening. And are we going to feel that? Well, when the earthquake happened back in the 1800s, there was actually reports of church bells ringing. So if you go to Milwaukee, Milwaukee's quite a ways up there. If I go back to the last picture, Milwaukee's a long ways up there, but there's actually reports of church bells ringing in Milwaukee. So if you go to a church and you go up to, to the top of the steeple, there was enough shaking going on back and forth that the bells were actually ringing. So when we look at these faults, this is a fault right here. It's hard to picture, but that's a fault. So you might be out in the desert, you might be, out in a four-wheeler, you might go over it and you don't even know that you went over a fault. Here's another interesting thing that happened. This used to be straight, but over time, things are shifting. Things are moving. Look at this building right here. This is in Japan. So the whole building was built on solid or non-solid. It didn't have a solid foundation, I guess is what I'm trying to say. And now the whole building is shifting, and it's going to have to be torn down before it falls down. Now here's one of the sad things. A lot of places do not have seismic safe structures. They don't have strict building codes. So that's why in a lot of countries that don't have these strict building codes, a lot of people end up dying. Much more than that would die here in the United States just because they have such weak building codes. This is interesting. Look at this line. Here's the yellow line on this side. Here's the yellow line over here. So we can see that the whole ground, the whole ground shifted, it looks to be about 8 to 10 feet. Look at this bridge up here. Double-decker bridge, one of the decks dropped. So again, if you're driving through there at night and all of a sudden you come down and you're going to hit that. Again, more damage that occurred because of an earthquake. Here's the Kobe earthquake. You might be wondering what we're looking at here, but here's the highway. This whole highway just basically fell over sideways as a result of the earthquake that happened. So where is the Kobe? Kobe is actually in Japan. And if you remember, Japan is on the very edge of the Pacific Plate and the Eurasian Plate. And you might say, well, golly, poor Kobe, poor Japan, they always have volcanoes, they have earthquakes. Well, yeah, it's not necessarily good that they have all this, but Japan would not be there if it wasn't for plate tectonics. So yes, the earthquakes and the volcanoes are bad, but yet Japan would not exist without this plate interaction. And the Kobe earthquake, actually 5,000 people died. Another 100,000 estimated were injured. And I think there's a little animation going on here. Let me hit this. So this is where the earthquake happened. And Kobe is actually way over here. So Kobe was not even right where the earthquake happened. It was actually a ways away. Again, earthquakes don't always cause the most damage. A lot of damage can occur for other reasons, such as ruptured gas lines that burn down these houses. Now, a lot of people are starting to build seismic safe structures that will withstand an earthquake. So this lady's put this bed together so that if an earthquake would occur and the ceiling would come down, or if she's in an apartment complex, if there's apartments above her, this would actually save her life so she wouldn't be crushed to death. And this building was retrofitted with these steel beams. And the whole idea behind this is they want this whole building to move together. If the building moves together, it's going to withstand. What they don't want is the bottom moving one way and the top moving a different way, because then the building is going to be ripped apart. This does conclude part 2 of our notes, and we'll start out part 3 with talking about the results of earthquakes, and we're going to take a look at seismic waves. Again, as always, if you have any questions, please ask your science teacher. Thank you, and goodbye.